tutorial I will show you how you can create computational fluid dynamics simulation using Salome Mecha for pre-processing and Code-Saturne for solution. So we'll start with the pre-processing phase. We'll open up Salome Mecha here. Actually, we will load an existing case that is called the pipe.hdf. And this case has already been prepared, so if you want to have a look at how you can get to that point, you can load flash videos that I already prepared for previous versions of CAELinux. So these videos, just for you to know, it's in CAELinux tutorials, pipe folder, and these are the pipe.geom.swf and pipe mesh. So we start with an existing case, so we need to start by loading this file. So we open, go to computer, root, opt, CAELinux, docs, tutorials, and pipe folder. So there are two files here, one with the geometry only and the other with geometry and mesh, pipe1 mesh.hdf. So we load this one. I switch to the geometry module here so that we can have a look at the CAD geometry of the problem. I expand the tree so that we can see the latest model here, Fuse 1, and we show the object and rescale the view. So that's it. That's how it looks like in wireframe mode, and here in shading mode. So you right click, select shading. So that's a pipe, a wide junction, cylindrical sections, and we already prepared groups for simulation. The first group is walls here. If I show it, it's the external surface of the pipe, and we'll have also a face called F1, which is the inlet here, and two other faces which are F1 and F2, F2 and F3, sorry, which are the outlets there. That's it for the geometry module, but it's important to notice that you need groups of geometry to then create groups of mesh elements for simulation. So we move then to mesh module. Yeah, it takes some time to load. Okay. So here is the mesh that we have generated. It's a tetrahedral mesh that contains about 66, let's see this, 66,000 cells, mesh information, yeah, 66,000 tetrahedra. So it's a fairly simple mesh to generate because it's uniform mesh size, tetrahedral mesh, so fairly simple. So that's how it looks like. And then we have already created a group of faces for wall, you see it here, for inlets, and for the two outlets. These are here actually. Yeah, these two. Okay, so that's for the initial setup. As mentioned earlier, look at the flash video if you want to know how to get there. So we need to set up a case for Code-Saturne now. So to do that, we will write the mesh in a MED file. MED file is a format that is used to exchange meshes between mostly Salome and Code-Saturne, and Salome and Code-Saturne. So we go in our home folder, we create a small folder for this analysis, CFD Saturne, that's it. And in this folder we'll create a med file that is called pipe.med for the mesh. So that's it, we have written the mesh. Now we can leave Salome. So I've just reduced Salome here. We go back to CAELinux menu, and here I will use the little wizard that I've coded for CAELinux. If you want to learn how to use the Code-Saturne in depth, you should really read the Code-Saturne tutorials, the official ones. But this is a short introduction. So we'll use just our wizard here. And then we need to fill a couple of fields. First, the study name is the name of a subfolder that will be created to store all the simulation files. Then the case name is normally, here we have only a single case study, so I will just call it case 1. And then the base directory in which you will create the study folder. So I will go in CFD-Saturne and validate. Finally, we need a mesh file in MED format. So I will pick the mesh that we have been just exported. So here, type MED and validate. That's all for the wizard. We click OK. Then the wizard is actually preparing a folder structure and then launching the Code-Saturne graphical user interface that you can see here. So this Code-Saturne graphical user interface is a relatively simple user interface in which you need just to follow each step in this tree from very first definition of the meshes and folders you are working on, and that ends up here with calculation management to the job management. So we go here first, mesh selection. You see you already have pipe.med in the mesh selection, so you don't need to do anything here. Then mesh quality criteria. That's a very important step. Actually, first because we need to check if the mesh is valid, and second because it will generate a list of groups to apply boundary conditions. So that's a step that you shouldn't skip. So you go here and press check mesh. And by pressing that, the preprocessor of Saturne is running, so you get a listing here of the statistics of the mesh. And this listing will be used afterwards to assign boundary conditions, so it's important to save it in a known location. So we are here, we save it in the result directory, we call it list pre. Yeah, that's it. And if you want to have a look at the histogram, the volume, angles, and so on, it's all written here. Then we move to the physics. So thermophysical models. First, calculation features will run a steady flow simulation, single phase, without any complicated physical model. Mobile mesh, we leave it off. There's no mobile domain. Turbulence model, we will run laminar simulation, so we turn off turbulence. Laminar model here. And thermal model, there's no thermal scatter, so there's no temperature field, it's isothermal. Then additional scalars, there's no additional scalars, so the additional scalars can be used to typically to compute transport of some quantities. So we leave this blank and we move to physical properties. So just to mention about the units, we prepared the case using meter units. So the mesh geometry is written in meters units in terms of dimension. So we'll use a coherent system of units of Pascal and so on. So the standard, so the SI, International System of Units. So reference pressure is atmospheric pressure in Pascal. Then fluid properties. So I will use a viscous fluid that has the same density as water, so 1000 kilogram per cubic meter density, and viscosity of 1. So it's fairly viscous. And for specific heat, I will just put the 4800, even if it's not used, because it's only for when you have temperature in the model, but still. Gravity, then I will ignore gravity here and move to the next part. Volume conditions, if you have several different volumes that are attached together, you may need to look at this, but Here we have a single volume, so we just skip it. Initialization is the initial velocity in your volume. Here we start with a 0 velocity. And add losses is if you want to have specific regions with empirical pressure drops, so add losses that you want to introduce, typically for porous flow or things like that. Then boundary condition, that's where we really need to input what is the physics of the problem. So boundary condition, we need to start by importing the listing of the preprocessor here. We are already in the result directory, but we just need to select all files, and we have our list pre file. And the good thing with this file is that it contains already a description of all boundary condition regions. So we can just then select which kind of boundary condition we assign to each group. So obviously walls is already selected as type wall, that's fine. And then F1, F2 and F3 should be set as inlet and outlet. We'll just have a look at the Salome mesh, and yeah, here. So if you remember well, I will just resize Salome, yeah, here. If you remember well, F1 is our inlet, so show only, that's our inlet, and then F2 and F3 are the outlets here. So if we go back to Code-Saturne wizard, okay, we'll double click here in front of F1 to set that F1 is inlet, and then double click here for F2 and set it as outlet, and same for F3. That's it for this phase. We have selected the kind of boundary condition for each region. Then we move to the properties of this boundary condition here in boundary conditions. So for wall boundary condition, here we'll use a smooth wall, non-sliding, so perfect. So the flow is attached. There's zero velocity on the wall. And then inlet, we'll use a normal velocity, so a velocity of 1 meter per second, normal to the input phase, so normal to F1, so equal to 1 meter per second. So we leave this like that, it's fine. And then for the outlet, there's nothing to specify because outlet means zero external pressure. Then steady flow management, that's where you need to specify how many iterations you run to reach a steady state. So it's important that you do a convergence check on this number of iterations. You should reach a steady value. If it's not the case, you need to increase the number of iterations. I will start with 100 iterations here because I know that it should converge for this number of iterations. And so that's it, but be careful with this parameter. Then equations, I will leave the default solver precision. It's very strict, but we leave it. And same for the scheme. And then global parameters, I leave everything default, but you can read Code-Saturne documentation to learn more on that. And then calculation control, time average, there's obviously no need for time averaging because it's a steady state. Output control, this is an important one. We need to say that we want, so first listing is a text output and post-processing is a field output. So for post-processing, we will ask an output every 10 iteration, post-processing every n time steps. And then about the post-processing format, we'll ask for a MED output. So you can use Nsight Gold format to post-process in ParaView, and you can use MED format to post-process in Salome. So that's what we will do for this case. So I leave this here. Then volume solution control and profiles will leave this empty. Once again, read the tutorials to learn how to use it. Then start or restart here in calculation management. It's not a restart, so it's the first run. We leave it like that, but you can change the restart settings here in advanced options, so how many checkpoints you write to the disk and so on. And then prepare batch calculation is where we specify how to run the simulation. So first it's on a local workstation, it's not on cluster. So we select the profile workstation. Then number of CPUs, here I will use 4 as I have a quad-core computer. And then advanced options, you can select, for example, where you put here the temporary files, if there's a place where you want to keep these files. So, but that's all. Normally you don't need to change that. So fine, we need to save the case now. So here, click on save and give it a name. So the case are in XML form, so format, so we call it case1.xml. That's it. So now we can run the simulation by pressing run Code-Saturne batch job, and you will see here that the CPU load is increasing, and actually the solution is running in background. So you can have a look in the terminal here to see some general messages about solution, but I will pause now the video until it converges. Okay, so here we are back again. So you can see here in the terminal that normal simulation finish means, okay, everything went fine. It doesn't mean it has converged, at least it means that there was no error. So if you want to have a look at what happened during the run, so you need to open the listing of the solver. To do that, we need to go to the simulation directory, CFD Saturne, the study name, pipe, the case name, case 1, and result directory. In this folder, you will see files that are always postfixed with a time and date here number, so that every time you run a simulation, actually you don't overwrite the files. You get another set of files. So the file we will be looking is listing with the time code here. We open it in the text editor and you can read it. It can be very valuable if you want to learn first if your mesh is valid, what happened during simulation, and convergence of the problem and so on. So this is the starting point, the pre-processing, and then your main calculation is the time stepping. So you can see typically the mass flow, balance, and so on, and information about the convergence of the. So if you have a problem with convergence of some solvers, you will get warnings and errors here. So that's all. I will not go further with this. Now we need to have a look at the field output, so to visualize the flow. So I will go back, we'll go back to Salome here. That's it. And yeah, we'll right click and say hide all, and then move to post-processing module here. Yeah, make some space here. So that's fine. Now we can load our result file. So we go in File here, Import, Medfile, and we go in the case directory, so pipe, case 1, and result, resu. You don't see the result yet because it is named a bit differently. It's not named .med. It is actually this file that contains the field. It's CHR means the field of results, med with the time code. So we open this, and in this file actually you will get the mesh plus the different fields of solution. So first, if we expand it, you see fluid volume, that's for the output on the cells, the volumetric cells. And then families, you can see actually the mesh here. If you right click on cells and say create presentation, you can see the input mesh actually. That's for the mesh. And then for the fields, you can see here pressure, and with under pressure you have different time steps. So these are pseudo time because it's a steady state solution. So we right click on pressure and we'll see how the pressure evolves during the simulation. So we'll select visualization mode, we'll right click. So we have scalar map, it's to see the field on the external surface of the mesh, isosurface or cutting planes to see internally what happens, and yeah, cut lines to get typically plots, 2D plots. Okay, so scalar map. I will leave everything to default. You can specify the range, number of colors, the size of the color bar, and so on. I will leave everything to default. So that's it. A representation will be created. It's available here. You can hide it or display it like that. I will just rescale the view. That's it. And then we want to scroll to step in time to see the evolution. So we go here, we ask for the slider. Slider is the time control, and we just drag it here so that it doesn't take the whole window. That's it. So we can see here we are at the time step 10 now, and we just press play to see how the pressure evolves during simulation. So you can see that actually I'm not sure we have reached a proper steady state because the last time steps there's still some evolution. So it's maybe better to run a longer simulation with more iterations in that case. So that's how you can see. So you see here the pressure field here in pascals like this. You can add, if you right click on the presentation, you can add shading to the view. That's nice. And now we'll have a look at the velocity profile on a mid-plane of the pipe. So we go to Object Browser. Then we'll select the velocity profile like this. Right click and we'll ask for a cutting plane view, so cut plane. The cutting plane will be parallel to XY plane, so we select this one, and we want just a single cutting plane here, number of planes equal to 1. And you can see with show preview, you can normally see the plane, so I will just disable the previous plot here. I cannot disable it from now anyway. In principle, you can see a preview by this, so you can see where the plane is. I accept it, and then I will hide the scalar map here to see only the cutting plane. So that's the velocity profile. You will see that actually Saturn is writing data only at cell center. So you see a constant value in each tetrahedra. So that doesn't give you an extremely smooth output. But if you load this MED file using Paravis here, the ParaView post-processor that is embedded in the new version of Salome, you can then compute the scalar field at nodes and get a smoother output if you want. But that's it for the present visualization, and we can edit the position of this plane here, changing it to 0.3 for example, and you have another cutting plane view. What is interesting also is to have a look at maybe the isosurface of velocity profile. So you can go here, say isosurfaces on velocity. We want maybe 3 isosurfaces and with a custom range. So typically we would like to see the velocity profile between 1, which is the inlet velocity, and the maximum velocity. So, and then magnitude coloring to see this isosurface in colors. So that's what you get. Here, it's not very visible because we should add some shading. So these are the isosurfaces of the flow for different velocities. So I can add some transparency as well. Right-click transparency so that we can see what is inside. So for example, like this. So you see that this first isosurface is for 1 meter per second, and so you see how the flow of 1 meter per second is distributed spatially. And we can change the isosurfaces to have a better view. I will just ask for a single one at let's say 1.5.5, something like this, or maybe a bit less, 1.2. Okay, so you see that this is the isosurface for velocity 1.2. I've not mentioned about the time step now because we are not at the last time step, so we are yeah, we need to go through. So that's, sorry, yeah, I've not selected the right one. Yeah, that's it. I've selected the isosurface and I will animate the isosurface for the different time steps. So you can see that during the iteration you have an evolution of the velocity profile that gives you this this trend. Okay, so you can see that in the last iteration the field doesn't move so much, but still we may need to add a couple of iterations, maybe some 200 iterations to reach a perfect steady state. So that's it for this video. I hope that you learned a lot, and at least that it will simplify your first steps using Code-Saturne and Salome Mecha. And so if you want to learn more on that field, you can visit us at CAELinux.com or CAELinux.org for the wiki, and where you can actually contribute with your own experience as well. So thanks a lot, and